What's good, math family? In this video, we're looking at transformations of quadratic functions. We're going to touch on 3 examples of how to properly do vertical stretches and compressions. In our first example, family, they gave us the quadratic function in standard form. So what we're going to want to do is just to convert this to vertex form. So after I subtract 13, we're going to have 3x squared plus 12x is equal to negative 13. We're going to just complete the square so we could go to vertex form. So after I pull out this 3, I'm going to have x squared plus 4x is equal to negative 13. So now at this step, we're focusing on what's inside the parentheses. And now I'm going to complete the square by taking half of 4 and squaring it. So we'll have x squared plus 4x plus 4. Now, when we add it on the other side of 13, just remember we have a 3 on the outside, meaning we have to multiply. So when we combine, we actually added 12. So from this instance, we clean up both sides. The left side, 3 stays the same. We break this binomial down to x plus trinomial, We break the trinomial down to its binomial, which is x plus 2 squared, and this is equal to negative 1. Now we bring the 1 over and set this equal to 0. And now we are able to graph this because it is in vertex form. So when we look at and this should be a positive 1. So now when we look at the graph, we should know that our vertex is going to be at negative 2, 1. So when I go over to my graph, this is where my vertex should be. Now, when we're trying to find other points, we cannot just use a regular transformation for the other points. We're going to have to use a table. So when we set this table up now, this is what we should have. So we already know that when x is negative 2, our y is positive 1. So we're going to find the y coordinates for negative 3 and negative 1. So now once we do this, this is going to help us with the transformation. So we plug this in. So we have 3 times negative 3 plus 2 squared plus 1. When we simplify this, negative 1 squared is just 1 times 3 is 3. And then when we add 1 more, this is going to be equal to 4. And the beautiful thing about this is that 3 and 1 are going to share the same y-intercept. This is why it's important to understand the axis of symmetry. So when we go in, we could plot those 2 points. So we're at negative 3, 4, which is right here. Right, we're in red, and then we're at negative 1, 4. So right now, as we look at this function, we could tell that this graph did have a vertical stretch because it's going to be much more narrower compared to the regular graph y is equal to x squared. So in the next example, we're lucky because we have the quadratic function in vertex form. So the first thing we're going to start off with is always the vertex, 3, 5. 2 and 4 are going to have the same y coordinate as well as 1 and 5. So you do not have to do the work for all of them, just at least 2 points. So we go in now and we're going to algebraically trying to figure out what are these y coordinates going to be when we plug the x in. So when we look at this now, I'm just going to do when x is 5 and when x is 4. So when we look at this problem now, we know that 4 times 4 minus 3 squared plus 5. When we simplify this, we're going to have 4 minus 3 is 1. 1 squared is 1 times 4 is 4. 4 plus 5 is going to give me a 9. So I know my y coordinate is going to be 4, 9, which would be, off our graph, but right here. And then our other one for 2, because they have the same y coordinate, is also going to be 9 as well. So right now we have 3 points, but we're going to get 2 more just for practice. So now let's say if we plugged in 5. So we plug 5 in for x. And what we get is 5 minus 3 is 2 squared. That's 4. 4 times 4 is 16. 16 plus 5 gives me 21. So I know the y coordinate for when x is 1 and 5 are going to be 21. So that doesn't fit on our graph, but let's just say that somewhere right here. We're just going to sketch it out for the video sake. So when we look at this problem now, we notice that this graph is a lot more narrow than the original parent function, which is y is equal to x squared. So when we're graphing these compressions and stretches, family, it's always important that you use a table and you don't have to do every point. Just do at least 2 points to the right or 2 to the left. And remember that they share the same y coordinate because of the axis of symmetry. And now we're going to go over to how to handle a vertical compression. Last problem of this video, math family, and if you have found this helpful, we do ask that you hit the like button, comment down below for us. So unlike the other two, because of this negative sign, we know that this graph is going to be opening down, meaning there is a reflection over the x-axis. If they had the function written different, as in f of x is equal to, and then in parentheses, they had negative 1/2 x squared, like what you see on my screen, this would be a reflection over the y. But with quadratic functions, that reflection, there's no change. So please don't fall for that trick. So our origin is going to be the same. It's going to stay at 0, 0. So now what we're trying to figure out is, what is our x values going to be? Our y value is going to be when we plug in x's such as -2, -1, 1, or even 2. So we're going to create a table. That is always the best way to do this when we have a vertical stretch or compression. So now we're going to plug in our x values. So let's write this. So we already know 0, 0. Let's do -2. And let's just do -1. So once we do this now, we have -1/2 times -2 squared. So we know that what? 2 squared is going to be a positive number. That's 4. Half of 4 is going to be -2. So I know off rip, when x is -2, my y is going to be -2. And I know the same thing occurs when x is 2. Its y value is also going to be -2 because of that axis of symmetry. They share the same y coordinates because they're the same distance from the vertex. Now, when we go over to 1, we're going to repeat this process. So we know -1 squared is 1. When we multiply 1 by half, we're going to get -0.5, or you could just say -1/2. So when I go in now and x is 1 or -1, the y coordinate is going to be somewhere right here where you see these purple points on my screen. Now that we have these points, we could go ahead and connect them and draw a parabola. And compared to the other two examples, you see that this one does have a vertical compression, meaning it opens up much more wider than the previous two examples. We really hope that this quick review on vertical stretches and compressions was helpful, math family. If it was, smash the like button for us, subscribe to the channel, and leave comments down below for future videos you guys would like to see in our channel. Or if you had questions on today's video, don't forget to stick around and look for our next video coming out on horizontal compressions and stretches. Thank you for joining.